In this video, we'll talk about solving congruences. So we're gonna define what do we mean by congruences, and we'll talk about an interesting theorem called the Chinese remainder theorem, which is used to solve a system of congruences. So we start by some lemmas that we may need when we are solving these congruences. First, if you have, you consider these lemmas, you can think of these as some exercises as well. So this is something that you can expect in your exam or some similar problems. If a, b, and c are positive integers, and we know that the GCD of a and b is equal to 1, and we know that a divides bc, then a divides c. So just to think about this using numerical values. Suppose that I have a equal to 6, and let's say I have b equal to 7. So clearly you can see that the GCD of a and b is equal to 1. Now we know that 6 divides 42, or we can pick something else. Let's say for example any number that's multiple of 6, let's say 84. 6 divides 7 multiplied by 12. Okay, so 6 divides 84, 7 times 12. Because GCD of 6 and 7 is equal to 1, then this implies that 6 divides the other number, which is 12. Okay. So as long as A and B have nothing in common, and you know that A divides BC, then A has to divide C. Now this is not true if the GCD of AB is not equal to 1. For example, I know that 6 divides 2 multiplied by 3. Okay? Or let's say 4 multiplied by 3, which is 12. But 6 does not divide 3, and 6 does not divide 4. The reason this doesn't work because this condition is not satisfied. So this is the key here to be able to write this. So here's the proof. We're going to use the fundamental theorem of arithmetic. We know that a can be written in this form, which is the prime factorization of a, and it's unique. This is very important. Now, because the GCD of a and b is equal to 1, so none of these prime factors appears in the prime factorization of b. So b, when you want to write b as a prime factor, using the prime factorization, none of these p1s is going to occur here. So P1, P2, up to Pn, they will not show up in the prime factorization. So here it's going to be like a Q1 times Q2 times Qm to some power, let's say B1, B2, Bm. But every Q is different than every P. So no two common factors because the GCD is 1. So what does it mean now? This means, for example, that A divides BC, okay? So the prime factors, all these is going to divide BC, but none of them divides B because all of them are different. So each of these prime factors has to divide C. So for example, Pi to the power AI has to divide C for I equal 1 to n. So each one of these has to divide C. Okay, so that means A equal the product of these prime factors is going to divide C. Okay. Another theorem here that we would like to prove is the following. If AC is congruent to BC mod M, and we know that the GCD of C and M is equal to 1, then it's like you can divide by C both sides. Okay. When we talked about congruences, I said you cannot divide, and I gave a counterexample. But actually you can, and that counterexample, if you look back at that counterexample, the GCD between C and M wasn't 1. Okay, So here, if the GCD between C and M is 1, then yes, you can divide. Okay, so here's the proof. We start by the definition of what does it mean to say that C is congruent to BC mod M. This means that M divides their difference, AC minus BC. Factor out the C, that means M divides C times A minus B. Now, we know that the GCD of C and M is equal to 1. So M and C have nothing in common, and M divides C times this guy. So by the previous lemma that we proved in the previous slides, then M has to divide A minus B. Now M divides A minus B. This is the definition of A congruent to B mod M. Okay. So now we define the meaning of a congruence, a linear congruence. So this should you can compare this to a linear equation. You know, linear equation is of the form ax equal b. This is what we called in algebra linear equation. So the linear congruence is kind of similar, but it's a congruence. So instead of the equal sign, you have a congruence. And once you have a congruence, you have to have a modulo. So ax congruent to b mod m is called a linear congruence. M has to be a positive integer. X is the variable, a and b are given integers. The solutions to a linear equation are all integers x satisfying the congruence. So it's like the solution of an equation is the values that will make the equation true. Same thing here. And you will note that we will have infinitely many solutions for these values, but we have like a specific form for these solutions. It's not going to be just any x. This is very important, and you will see that we will focus on a special type of congruences when the GCD of A and M is equal to 1. Now, before we start solving, we define something called the inverse of a number. So an integer a bar such that a bar multiplied by a is equal to 1 modulo m, or congruent to 1 modulo m, we say that this integer a bar is the inverse of a modulo m. So a bar is called the inverse of a modulo m. Okay. For example, 5 is the inverse of 3 modulo 7. So this is like a, and this is a bar. Okay. Why? Because if you multiply 5 by 3 mod 7, you're gonna get 15. You're gonna get 15, which is 1. 5 times the 3 is congruent to 15, congruent to 1. Why? Because you reduce modulo 7. 15 modulo 7 is 1. The quotient 2, the remainder is 1. Okay. So we will use the idea of inverses to solve linear congruences. So here's a theorem. If GCD of AM is equal to 1, then an inverse of A modulo M exists. So you don't always have an inverse. You can only have an inverse if the GCD of AM is 1. Furthermore, the inverse is unique modulo M. If the GCD between A and M is not 1, then we do have many inverses. We're not going to see this case. So you're going to see only the cases when the GCD between A and M is equal to 1. So to solve linear congruences, we won't divide by A, because I cannot divide by A. I don't know if B over A is going to be an integer or no. But what we can do instead, we will multiply by the inverse on both sides. Okay, so the idea is this: you have AX congruent to B mod M. Okay, you're gonna have GCD of A and M is equal to 1. By this theorem above, then A bar exists. So the inverse exists. So what do we mean by this? We have to find A bar first. After you find A bar, you multiply both sides by A bar. Now, a bar multiplied by a, that's going to be congruent to 1 modulo m. So this is going to be 1. So that's going to make it x congruent to a bar b mod m. So I isolated x by itself here. This is something that I can find because these are just some integers. I can find them, I can reduce them modulo m, and then I can write my solution. Okay, so the key is what? Is to find a bar, which is the inverse. So once we find the inverse, then we can solve the linear congruence. So how do we find the inverse? Now, if the numbers are small, or then we can do this by trial and error, and that's okay. Like for example, suppose that you want to find the inverse of 3 or 4 modulo 5. Okay, so in other words, so this is A, you want to find a bar. So in other words, you want to find a bar so that a multiplied by a bar is congruent to 1 mod 5. That's the inverse. So you want to find a bar times 4 congruent to 1 mod 5. Now I know for sure that a bar exists because the GCD of 4 and 5 is equal to 1. Now, what are the possibilities here? You don't have many possibilities. Okay, the possibilities for a bar are either, because I'm working on mod 5, so the possibilities are 1, 2, 3, and 4. And this is not too many options, so you can just do this by trial and error. For example, that's not going to be 1, because 1 times 4 is 4. It's not 1 mod 5, so it's not 1. Is it 2? 2 times 4 is 8. If you reduce 8 modulo 5, it's going to be 3. So this is not the case. Remember, I want my answer to be 1. 3 times 4, if a bar is equal to 3, then 3 times 4 is 12. When you reduce 12 modulo 5, you're going to get 2. Okay, so that's not the case. So this should be the case. Verify. If you choose a bar to be 4, so now it looks like a and a bar are the same number, but it's going to work because 4 multiplied by 4 is 16, and 16 modulo 5 is 1. Okay, so here by trial and error, I was able to find it. So a bar is congruent to 4 mod 5. So you can choose a bar to be 4. So this is how you can find it by trial and error. This is efficient if the numbers are, if you don't have lots of possibilities. Okay, but if you have bigger numbers, then we need a nice method to do this. So here's how we're gonna find the inverses. Okay, so we're gonna use the Euclidean algorithm and the extended Euclidean algorithm to find the inverses. So here's the idea. I want to find an inverse of 55 modulo 89. So in other words, I'm looking for the following number. So we need to find, let's call it x, okay, such that if I multiply 55 and x, I get 1 mod 89. This is my goal. My goal is to find this x. Okay, now this means what? This means the following. By the definition of congruences, this means that 55 multiplied by x is equal to 1 plus 89 multiplied by some constant. I'm going to call it k, where k is some constant. We have proved this theorem before, and we have used this definition, or this it wasn't a formal definition, that was a theorem, and I said we can use it as a definition because it's very efficient and very nice in practice. Okay, so this means the following, that 55 multiplied by x minus 89 multiplied by k is equal to 1. Let me write this in this form. This means that 55 multiplied by x plus 89 multiplied by negative k is equal to 1. Okay, but here, hold on a second, there's something familiar here. I know the GCD of 55, actually I cannot talk about inverse unless the GCD is 1. I know, so here on the other hand, I know that the GCD of 89 and 55 is equal to 1. Okay, so by Bezout theorem, that means there exists ST in Z. Do you remember the S and T from the extended Euclidean algorithm? Such that 89 multiplied by S plus 55 multiplied by T is equal to 1. And in theorem, we say that these S and T are unique. Okay, you can't have another different values for S or different values for T. Well, if I compare this equation with this equation, this is actually the same, except that instead of negative k here, I have S. Instead of T, I have X. Oh, but hold on. My concern was finding X only. So in other words, I just need to find the S and T, how I used to find using the extended Euclidean algorithm, and what I care about is only the value of T. So that's going to be the inverse. Okay, so here's the idea. That's how we're going to find it. We're going to divide 89 by 55. Using the Euclidean algorithm, we should expect the GCD to be 1. And then using the extended Euclidean algorithm, we're going to find the value of T. I don't care about S because you see I care about T. And always, that number, if it's bigger than 89, you reduce it modulo 89. So this is going to be my A, this is going to be my B, and then I will use the Euclidean algorithm. So here's how I do it. So here A, as you can see, A is 89, always the big number, so that we have the same notation. B is 55. And then look, I'm not putting a column for SK because I don't need it. I only need TK, which is the number that will be multiplied by the small number B, which is 55. This is the setup for TK, T0, and T1. And then I start my process, the regular Euclidean algorithm. You're going to do the Euclidean algorithm first. You're going to find that the GCD is equal to 1. And this is expected. Okay. And then I use the extended Euclidean algorithm to find the value of tk, which is going to be this. That's the last step, 34. So this is t. So that means the inverse of 55 modulo 89 is equal to 34. And to verify, take 55, multiply it by 34. We should expect, we can verify this, that this is congruent to 1 mod 89. Okay. So to verify this, do 55 times 34. So 55 times 34, this is 1870. Divided by 89. 1870 divided by 89. It's 21. So I'm just doing this using the calculator. Now 21 times 89 is 1869. Subtract, you get 1. That's the remainder, and that's what we expected. So the inverse of 55 modulo 89 is equal to 34. That's one inverse. You can have many inverses. How? You can keep adding 89 to 34 because, you know, when you work in mod 89, 89 is equal to 0 mod 89 or congruent to 0 mod 89. So you can add as much as you want 89s and subtract as much as you want 89s. So that's why here it says find an inverse, because there's infinitely many inverses in this case. But there's only one inverse between 0 and 89. And that's the only, that's the smallest positive inverse. And that's what we care about. Now, as I said before, once you have the inverse, then you can solve, well, you have the inverse of 55 mod 89, then you can solve this easily. How? We know that the inverse of 55, it has to be mod 89. Mod 89 is 34 from the previous example. So now multiply both sides by 34. Okay. So when I multiply by 34, I get this. 34 times 55 multiplied by x is congruent to 34 mod 3. Sorry, times 3 mod 89. This was one of the properties of modular. When we defined this, we have proved like properties. This was one of them. Like if A is congruent to B, then AC is congruent to BC. Of course, the same mod M. You don't multiply 89 by 3, or I mean by 34. Now I know that because these are inverses, that this is going to be 1. So the left-hand side is going to be just x, and the right-hand side will be 34 multiplied by 3, which is 102. Now I can reduce this mod 89. So 102, there's only 1, so minus 89 is equal to 13. So then x is congruent to 13 mod 89. This is my solution. Now this means what? This means that x is equal to 13 plus 89 times k, where k is any integer. So you have infinitely many solutions. Every value of k is going to give you a solution. But 13 is the smallest positive solution. Okay? So this is how we solve linear congruences.